Yep.
Sir, is
Yes,
it
tell
okay
me.
if you model in space gas? Because my bending moments in column is very small.
Sorry?
I modeled the project in space gas, and I'm getting like small bending moments in columns.
In the columns.
Yeah, for project. It's like only 13 kilonewton meter, the bending moment on the column.
Okay. Can you send that one? I will have a look. Um, okay. Then I will give a
Okay.
call to you after maybe tomorrow
Okay, sir.
morning. Okay. Yeah.
Thank you, sir.
Any other questions? Okay. So if not, so let's start this pre-stress. That's a relatively new um, new topic. So the PowerPoint I will update that one soon. So let's see. Okay. Okay. Um, so this is about the pre-stress design. Yeah. So far, we discussed about the reinforced concrete design. Over there, we look at how to determine the reinforcements for bending moment. That means longitudinal reinforcements and shear reinforcements, and we also look at how to check for deflection and cracks. Okay, so these are the main four checks we discussed in our previous section, which is reinforced things. So if you look at the reason or theory behind, so we look at very brief introduction about the concrete. As you know, the concrete is very weak in tension but have good compression capacity. So what we did in reinforced concrete design, we look at the tensile zones because the concrete can't take tension, so we look at the tensile zone and we provide some steel reinforcements or steel bars, so that the steel bars takes the tensile force or tensile stress while concrete take the compression. So we technically design the beams so we know what to do for the reinforced things. So this is another different techniques to overcome the weakness in the tensile capacity of the concrete. Okay, why we need to provide the reinforcement in the RCA design? Because concrete cannot take any tensile force, so we provide some steel so that the steel will take the tensile thing. So through that technique, okay, providing additional reinforcements in the tension zone, we overcome the issue. Okay, so if you look at that concrete, the plain concrete cannot take any tension or very little tension force, so we provide something to carry the tensile stresses. In this technique, this is completely different approach. We try to use the concept of pre-stress. Okay, so this is not a new technique, but we use this technique, the pre-stressing techniques, for a long time. Okay, even day-to-day life, if you have a set of books, to lift a set of books, what we do normally, we apply some compressive force, yeah, and lift it. So technically, if you don't press that one, or if you don't give the compressive force there, it will collapse. Yeah, so that is the normal day-to-day example. We use the concept of pre-stress. So we technically apply the compressive force. Okay, we apply some compressive force so that it will hold the load unless fail. Okay, so even if you look at this, the other example, the barrel. So we have wooden part, okay, and then we have the metal part, metal band. So if you don't have the metal part or metal band, when you put the water will give, okay, when you put the water will give outward pressure in the wooden staves. So you have outward pressure. So if you don't have any metal part there, that will break the assembly. Okay, because if you assemble like a barrel, the outward pressure from the water will break the assembly, so you can't hold the water. So what we do, we heat the metal, usually steel, so we heat the metals, and then metal will expand, metal ring will expand, and we put it over there, here, like two bands. Okay, so we heat it and put it there, and then we cool it. So what will happen, so the metal will shrink, so that will give a compressive force, because metal tried to tight, so that means give a compressive force to the wooden staves, then it will stay as it is. So even if you put some water, it won't collapse the assembly. So this concept is in use for a long time. It's not a new technique, but in concrete it is relatively new. Okay, in concrete it is relatively new. So what we do is, you can see this is the reinforced concrete section. If you have simple bending member, So generally the bottom part will be under tension, top part will be under compression. Okay, so if you have tensile stress at the bottom part, so we provide some reinforcement so that it will take tensile stress. Okay. Remember, when you provide reinforcement or reinforced bars, still we may have some small cracks. Okay, so the cracks might appear, but it will not progress to the failure. So in reinforcements there will be some cracks, as you know how to calculate the crack width. Yeah, you did the crack width calculation in reinforced concrete beam. So the cracks are there, but it's very small, so within the acceptable limit. Okay, but in the pre-stressed things, what we do is in the tension zone, wherever that we provide the reinforcement in the RC beams, we apply some compressive force. Okay, we apply some compressive force. So what we do is we try to apply some compressive force in the tension zone. Okay, the tension is at the bottom. Tension is at the bottom part because its beams bend downward. In this example, beam bends downward. Yeah, the beam bends downwards in this example. So we will see the bottom part will be under tension. So we apply some compressive force in the bottom zone. Okay, that means below the neutral axis. Below the neutral axis, because below the neutral axis will have tension. So we apply some compressive force. Okay, now we don't have any loading, so we are constructing the beams. So we apply some compressive force. So when you apply some compressive force in a beam without any loads, okay, only dead load or self weight of the beam is there, so we apply some compressive force. So since you apply the compressive force below the neutral axis, so the beam will bend upward. Okay, you can try that one with then some sponge kind of things. Okay, if you take a sponge rubber beam or a small sponge, normally we use to wash the car or something, the rectangular sponge, you can apply a compressive force below the neutral axis, below the halfway, and you try to push that one. So you can see while the bottom part compress a little bit, the top part will bend upward, so the overall beam will bend upward. So at the moment this is a construction time, so we don't have any loads on the beam, but we apply the compressive force, so the beam will bend upward. Okay, so now we apply the loads. Now we apply the load. So what will happen when you apply the load? What will happen? The beam bent upward, so we apply the load from the top, so it slowly comes down because it bent downward. Okay, so finally that will bend downward, but the deflection here, the deflection in this stage, okay, deflection at this stage will be much smaller than what we get in the RC, beam. Okay, because in the RC beam normally we have a flat beam and we apply the load, it will go downward. But in this case, in pre-stress one, before we apply the load, it's bent upward, so upward deflection. So then when you apply the load, it will comes down, become flat, then go down. So the initial upward deflection will reduce the overall or final deflection of the beam. So in pre-stress beam, we will have very less deflection under service load. Okay, when you put the service load, we will have very small deflection compared to RC beams. So the very less or small deflections, it's good because it will satisfy the deflection check easily, because small deflection means that will be well below the limit, so that's a good thing. But another advantage in the small deflection, so when the beam bends by a small deflection, so the tensile strength at the bottom fiber will be also less, because the bending is less, means the tensile stress will be less. So the chance of getting cracks will be less. Okay, so in this pre-stress concrete, we'll have a less deflection. That means we'll end up with almost small or no tensile stress, very small tensile stress. So the concrete, even though we said it can't take much compression, tensile strength, but it has some tensile strength, okay, very small. So if you have small tensile stress, that can't carried by concrete, okay, because tensile strength of the concrete is not zero. Okay? For ultimate case we take as a 0, but for serviceability case it will be some value, maybe 5 megapascal or 10 megapascal. There are some values. Okay, so when you have small tensile stress in the bottom fiber, that can take or that can carried by the concrete. So if concrete can carry that tensile stress, we will not get any tensile cracks. So in pre-stress, we introduce some compressive force in the bottom or tensile zone. So that will reduce the deflection. Less deflection means less tensile stress in the tensile fiber. The less tensile stress in the bottom fiber means the less chance of getting cracks. So no cracks in this one. So in pre-stress concrete, our criteria is limiting the crackings. Okay, limiting the crackings. In RC design, our limitation is with the deflection. Okay, if we assume a depth, how to ensure that is okay? So we use the deflection check. Okay, we use the deflection check to check the section. Yeah. So in this case, deflection is not a problem, because since we have an upward deflection at the start, our deflection, final deflection, will be much smaller. So our criteria here will be cracking. So we try to eliminate the cracks, in the tension zone. So we don't want to have any cracks, because with the less deflection we should be able to do that. Okay, so we try to reduce the cracks because we already know the deflection is less. So that makes, or that gives some advantages and disadvantages. So that is the concept we are going to use. So we apply some pre-stress force in the tension zone, so that actually it reduce the deflection, so that the tensile stress will be less, so that the cracking will be eliminated. Okay, so if you look at those idea or concept, you can see the pre-stressed concrete have advantages and disadvantages. Okay, everything have some merits and demerits. Okay, you can't have, or you can't say all the good things, that there are some disadvantages or issues. So we will look at both. The first one is a smaller deflection compared to RC beam, because we have upward or opposite deflection at the start of the loading. So the crackings will be eliminated, because smaller deflection means smaller tensile stress, that means no cracks. So if we can reduce the cracking or eliminate the cracking, so the section become uncracked section. You remember that one, the uncracked section? So that become uncracked section. So if you compare the cracked section and uncracked section under serviceability, we discussed those things, yeah, cracked section and uncracked section. If you calculate the I value, second moment of area, for uncracked section and the cracked section, which one is larger? The uncracked section will get larger I value. Okay, uncracked section will get larger I value, or larger second moment of area. So the larger I value means the stiffness will be large. Stiffness is EI. Stiffness equal to EI. E is the elastic modulus, I is the second moment of area. EI is the stiffness. So if you have no cracks, that become uncracked section. And in the RC design we discuss with some calculation about RC design, cracked section and uncracked section. So if you look at that uncracked section and the cracked section PowerPoints, we discussed that one, I think 2 or something, 2 or 3. Uncracked section will get larger I value, so that means it's have larger stiffness. Larger stiffness means difficult to bend. Okay, difficult to bend. Larger stiffness means difficult to bend. That means it have larger bending capacity. Okay, so by reducing or eliminating the cracks, we have lots of advantages. No cracks means larger stiffness or more stiffness. More stiffness means better bending capacity. Better bending capacity. So we can go for the longer spans. Then we can increase for the length of the beams, because it can carry lots of bending moment, because stiffness is better. So more stiffness means it will have better bending capacity. So we should go for larger span, or we can reduce the section height. If we have the fixed span, we may have lesser section, okay, because it has better bending capacity. So that is one thing. And if it is no cracks, what is another benefit? If you don't have cracks, there will be no corrosion problem, okay, because if you have cracks, only the water will go through that cracks and it will start to corrode, or it will have some other issues in the areas where you have zero temperature or below zero. Okay. So these are advantages, okay. And also, unlike the RC beams, you can cast the pre-stressed beams somewhere else and bring it to the site and assemble, okay. So pre-stressed concrete or precast concrete can be casted somewhere else and assembled at the site. So the faster construction, okay, the construction is quicker, because in RC construction you need to put the formworks at the site, yeah, you need to put the formworks and put the reinforcements and put the concrete. So that's take time, yeah. To the next level, you need to wait for 3 or 7 days to remove the formwork and we need to go further. So it will take time, but this one can be casted somewhere else and bring that beams to the site and assemble. So the faster construction. Okay, so these are the advantages. But what are the problems? The construction cost is much higher compared to RC, okay, because we need to apply some compressive force to the beam, okay. We'll see how to apply that one, but application of compression force costs money, okay. So the compressive force we need to apply is not 2 kilonewton or 3 kilonewton, okay. It is 1000 or 5000 kilonewtons. So it's very large compressive force we need to apply. So if you want to apply very large compressive force, you need to have very powerful jacks to apply something, yeah. So it's quite expensive compared to RC, okay. And also the error margin is small, so you can't say, if you say, for example, if you need, let's say if you need an RC beam, you will calculate the AST, the area of reinforcement. Let's say you need 100 millimeter square, so you can put 120 or 150. You can put some tolerance, yeah, because that even it's a little bit less, the design will have some tolerance, 5% tolerance is allowed. But in pre-stress, the error margin is very small, okay. So the error margin, and also it has some problem with the time dependent losses, because we construct today, the beam will stay for another 30 or 40 or 50 or 100 years, okay. As we go, there will be some losses. We will discuss that one later. What are the losses and why those losses are occurring? But as we go, after 30 years or 40 years, there will be some losses. So that need to be overcome. Okay, so that is one problem. Since the error margin is small, and the design is more complex. Okay. In other words, compared to RC design, this is a little bit more difficult. Okay. So actually not difficult, it's a complex. So you need to understand carefully, because the error margin is very, very small. you don't have lots of room to adjust. Okay, so let's see how we apply the pre-stress in a minute, and then we can discuss why the time dependent losses cause some issues. So these are some common examples of pre-stress beams. The pre-stress construction or pre-stress beams are mostly used in highway bridges. Okay, highway bridges in Australia, we don't have lots of highway bridges, elevated highway bridges, but usually in Japan and America, they use, most of the highways are elevated above the ground. Okay, so if you see, I'm not sure how many of you look at some countries have smaller bridges, okay, overhang bridges, but the highways, the entire highways goes on the elevated bridges. Okay, especially if you visit Tokyo, New York area, so you can see one highway will go this one and another one will go top of that, so something like that. So there will be lots of elevated bridges, so used as a highways. So for that, mostly they use pre-stress beams.
So in developing country also there is nowadays like they try to get the pre-stress bridge more often.
That's
with eye gutter and with the box gutter.
Yeah, box girders and everything. Yes. So we look at that one. So what I'm saying is, I don't say that developing countries don't have, but this is entire highways normally have elevated one.
Yeah.
And nowadays, because the problem is when you have limitation in the land, in Australia we don't have that problem. You can see that lots of lands are available, so they don't have much issues. So most of the highways or motorways are on ground, but if you don't have lots of lands, nowadays even in the Sydney area and Melbourne area, they start to build the bridges for the highway purpose. But
mainly, sir, in Nepal, I was the part of one company who was working in Nepal, and in Nepal there was the first pre-stage bridge. I was the part of that. So mainly in Nepal, they have like been trying to use in the river for the river crossing, not for the.
Yes.
They are trying to use for the river crossing because there are lots of river in Nepal. Sir.
Yes. So this one is very good for the longer span, especially. So if you want to put the bridge across the river, if it is RC beam, you may need to put a couple of columns inside or within that river, because we can't have longer spans. But this one can go longer spans. Sometimes we don't have any middle columns, or maybe less number of middle columns, depend on the width of the river and others. So we should be able to look at the longer spans. So you can see this is a bridge, highway bridge they use in USA. You can see there's a person standing here. I'm not sure whether you can see. So he is standing somewhere here, okay? One person. So you can see, based on his height, you can imagine the span of the bridge and the height of the bridge. So, and you can see the decks are very small thickness. The deck thickness are very small. So this is called a general term. This is called a column, and this part of the column is called headstock. Okay, headstock or bend caps. In USA they use as a bent, B-E-N-T, bent caps, or in Australia they use headstock. So that is sitting top of the column, and that spread the load. So this part is called bend caps or headstone. So they use pre-stressing things. This is another bridge in Japan, in Akihabara area. Akihabara is electric city of Tokyo. So you can see this built in 2007, I think, actually. So this one, pre-stress wires or tendons. Okay, you can see the pre-stress tendons. The special thing is this is epoxy coated steel. So all these steel tendons are coated with the epoxy. So because if you let the steel exposed to environment, it will easily corrode. So that will make some problems. So these ones is still it's exposed to environment. You can see the steel, but all are epoxy coated. So no direct contact with the environment for the steel. So that have longest lifetime, less maintenance. And this one is this both are same bridge, different views. This is actually a pedestrian bridge. Again, is in Tokyo. So the interesting part here, you can see the pre-stressing tenons outside. The deck is very thin deck. Okay, so I will explain this pre-stressing technique in a minute, but pre-stressing wires are outside the section, something like this, but it is well outside, and you can see it actually goes up here. It goes up. This is also pre-stressing tenon. Goes up and goes down again. So this is two-span pedestrian bridge. So I think this built in early 2000, early 2000 or 2001 or end of 1990s. So around that time. So that is external post tensioning. So I will explain that one in a minute. But it's called external post tensioning. So the pre-stressing wires are completely outside and connected through some connectors to the deck. So that's another example. So like that, we have different applications, but all the railway sleepers, concrete railway sleepers, use the pre-stressing techniques. None of them have reinforcement, so basically use the pre-stressing wires. And even nowadays they use in piles and the posts. Okay, so if you look at the materials, again we'll have only two materials like RC beams. There's no much different, concrete and steel. Okay. In RC design, the concrete and the steel is actually used as a reinforcement bars. So here the steel is mainly used as a tendons. Steel will provide some reinforcement, but steel mainly used as a tendons. Tendons are the ones we apply the pre-stressing force or compressive force to the concrete. Okay. So in this case, since the section is applied an external compressive force through steel tenons, so that it can carry large force or large bending moments. Okay, so we try to use the compressive capacity of concrete as much as possible. So in this design, in pre-stress or PC design, pre-stressed concrete. We use high strength concrete, normally more than 50 MPa. Okay, more than 50 MPa. Normally we don't use a 25 or 30. It's not very effective. Okay, so we like to have very large concrete. Currently we should be able to go up to 120. So this Akihabara bridge is use 120 MPa concrete. Okay, so they build using 120 MPa concrete, high strength concrete. So effectively they should be able to reduce the section height and everything. So the dimensions can be reduced significantly. And also in the concrete, as you know, when you place the concrete, it will take 28 days to get full strength. Yeah, normally to get the full strength we need to wait 28 days, but normally the construction will go with after 7 or 10 days, because the concrete strength will increase over the time. In first 7 days, within first 7 days, it will reach around 65% of concrete in normal PC concrete. Yeah. After 7 days, you can expect around 65% of the full strength. But in pre-stress, we would like to have that value a little bit higher. Okay, we would like to have that the strength gain in early days of the construction is much higher. We expect that. Okay, so we prefer high early strength. That means within 7 days we should be able to get 70% or more, so something like that. Okay, so in normal concrete around 65%. We like to get some early strength, because then we should be able to fast our pre-stress concrete construction. We'll talk about that one when we derive some equations. So I will explain that early strength gain at later stage as well. Okay, at this stage you may not get full reason why it is, but I will explain that one at a later stage, maybe next week or in the next class. The steel, so here again we use high strength steel, not like N-type. N-type is only 500, yeah, 500 MPa, but we will use high strength concrete. So these are the steel sections we use in pre-stress. So in RC design we call the steel as a reinforcement or reinforced bars. Yeah. Here we will call them as a tenons or strands or wires. 3 words. I will explain that in a minute. Wires, normal wires, or strands and tenons. Tenons, strands, wires. 3 words. I will explain in the next slides. Okay. So this one is some wedge. So this one used as a end connectors. Okay, I will show that one in the next slide. You should be able to understand why it is. So these are the main components, main materials. This is the steel. Properties of steel. This is the normal steel you come across in the RC. This is the PC one. Okay, very large capacity compared to the normal steel. So this steel is used to make wires. Okay, look at this wordings. So wires, and that other one is a strands. And the other one is tendons, as I mentioned here, the tendons. Okay, so three things. This is tendons and wires and strands. So what they do is, using steel or high strength steel, they manufacture wires. Okay, so you can see the wires here. This is called wire. Okay, so this one, so there are so there are 7 wires. You can see 7 wires. So this is one wire. Okay, so this is one wire. This is one wire. Okay, and we have 7 wires here. This is called strand. This the whole assemble things is called strand. So using multiple wires, it can be 2 wires or 3 wires or 4 wires, we can have strands. Okay, so just here 7 wires. Okay, 7 wire strand. So this is a very common used in presters in Australia. They use 5 millimeter wires. This is, each wires are 5 millimeter diameter. Okay, or 7 millimeter diameter. There are 2 different wires, either 7 or 5 millimeter. Okay, mostly 7 millimeter used here, but there are some 5 millimeters as well. So they use 5 or 7 millimeter wires, and then they use couple of wires to make strands. So again, 7 wire strands are most common. 7 wire strands are most common. 7 wire strands are most common. Okay, so couple of strands make a tendons. So this is called tendons. Okay, this one is called tendons. You can see there are a couple of strands, 1 2 3 4 5 6 9 10 11 12. I think 12 strands are here. Okay, 12 strands are here. This is called one tendon. Okay, so this is called one tendon. It will go like this. So this is this part you can see from outside, but this will go into the beam. Okay, you may not see all these wires, all these strands come like this into one single pipe. Yeah, it will go like that. So this part, the steel, there's here something like a steel part. Yeah, so that is called duct. D-U-C-T, duct. Okay, I will show that one in a next slide. Don't worry, D-U-C-T. So it's something like a wire. Something like a pipe. Okay, you can think something like a steel pipe. So this is called duct. It will go like long one. So this is how that arrangements in the pre-stressing will look like. Okay, so we have new terminology, as I told: wires, strands, and tendons. Okay, so in one pre-stress beam we will have a couple of tendons, maybe 5 tendons or 6 tendons. we'll quickly show that arrangement. Yeah, you can see there are 6 tenons. Okay, you can see there are 6 tenons. Each tenons will have some couple of different strands. Each strands may have couple of wires. Okay, so this is how normally we have the tenon arrangements. You have tenon arrangements, and this is something like a complete beam. Okay, yeah, so you have some idea how that looks like. Okay, let's see then how to apply the pressure force. As I told, what we are going to do, we are going to apply a compressive force to the concrete. Okay, we are going to apply a compressive force to the concrete. Okay, so there are 2 ways we can apply, or 2 techniques or 2 methods we use. The first one, look at this one. Okay, so what we do is we will take a steel, consider steel wire. Okay, so we take a steel wire and stretch that one. Okay, we fix here, this is a fixed end, and then this is another fixed end. Using jack, we pull that steel wire. Okay, what will happen? Steel will be under tension. Yeah, understand? It is very important to understand what's happening. So we stretch, or we pull the steel using jack, so the steel will be under tension. Okay, steel will be under tension because you pull that. Okay, yeah, so you pull that one, so you keep that one, it's under tension. Now you put the concrete. Okay, you put the concrete over there. Remember, steel is under tension. Okay, but it is fixed at both ends. So steel, you pull that one and fix at both ends and put the concrete. Then after 6 or 7 days, okay, not 28 days, we don't wait. After 7 days, we cut the wires. We cut here and there. Okay, so what will happen when you now look at the steel? Okay, you stretch the steel. So steel is under tension. Yeah, so you fix that one in both ends, and now you cut the wire. You cut that wires. So what will happen? If you don't have concrete, what will happen? The steel will go back. Yeah, because if you don't have concrete, the steel will go back to the original position, because you stretch the steel. Yeah, and if you release it, it will go back. Okay, you can think of rubber as well. Okay, you take a rubber band and you pull that one. If you release, it will go back. But now you release that one after putting concrete. What will happen? So steel wants to go back, but concrete won't let it go. Yeah, because steel wants to go back to the original position, but there are concrete. So concrete will not let the steel to go to the original. So what will happen? The steel will try to push the concrete. Okay, so we apply the compressive force. Okay, the steel tried to push the concrete because it want to go to its original place, original position. So we apply the compressive force to the concrete through the steel like this. Okay, so this is the actual construction of this one. So they stretch the steel, you can see they stretch the steel, and this mold side in the middle, they put the concrete, and after it hardened they will cut here. Okay, they will cut here, so this will go back to the steel tried to go back to the original position, but the concrete won't allow. Yeah, so we'll give, or the steel will give a compressive force to the concrete. So this is called pre-tensioning. Okay, this is called pre-tensioning because we apply tension force to the steel. We apply the tensile because we stretch the steel before putting concrete. Okay, so before putting concrete, the steel is stretched. Okay, before casting concrete, so that is called pre-tensioning. In the next one, almost similar setup, you can see what we do is we don't have any steel here now, we cast the concrete. Okay, we cast the concrete, but during the casting we put a pipe here that is called duct. This is what I mentioned, the steel pipe. Okay, so you see this is the duct.
Yeah.
Okay, so you can think of a pipe. So we put a pipe here or duct here. So during the construction we put a pipe there and put the concrete and cast it. So once it hardened, after 7 days or something, we insert a steel wire. Okay, we insert a steel wire and fix this side. Okay, we fix this side, and using jacks we pull that one because that comes through the pipe, so it can move. Yeah, steel can move, so we pull the steel from the other side, so that means we stretch the steel again. Okay, we are doing the same thing, but time is different. Okay, we stretch the steel and fix it here and release the jack. So once you fix that one and release the jack, steel tried to go back, but the concrete wouldn't allow that, so that will give, the steel will give a compressive force. Okay, you understand? So here, when you jack that one and to fix that one, we don't use the bolt. Okay, the bolt threads will go very quickly with the high force. Okay, so what we do is we use this wedge. Okay, so this is the same thing here, the wedges. You can see this wedge will help to fix the other end. So this is a wedge side. So when you put it down, so when you pull in the back side, so it will, the diameter will increase. Yeah, so it's difficult, so it will tighten the wires. Okay, so this is the wedge we have. So as you, when you pull from the other end, so the wedge try to go inside, but the diameter is increased, so that will compress the steel wires that go through that. Okay, so this is how we put the connection in the post tensioning. Why we call post tensioning? Because the post tensioning, because we are applying that
tension is done after casting, sir.
Yeah, after casting. Okay, so we stretch the steel after casting. Earlier we stretched the steel before the casting.
Yeah.
So that is called pre-tension, post-tension. okay, pre and post, but both are called pre-stressing. Pre-stressing is different. Pre-stressing, so that means pre-tension, post-tension, both are called pre-stressing. So two different techniques, okay, two different techniques comes under pre-stressing. Understand? So now let's move into one by one. What is the good thing with the pre-tension and what is the good thing with the post-tension things? Okay, so here these are two different techniques, okay, but both are comes under pre-stressing. You know how to apply the pre-stressing force, how to apply the pre-stressing force under both condition, yeah, under both techniques. So let's look at the pre-tension first. So the pre-tension have some benefits as well as some concerns. So as you know, in the pre-tension you stretch the steel, before you put the concrete. So from here to there the steel will have same tensile force, yeah, that steel will have same tensile force because there is no concrete or anything. So you take the steel and stretch that one, so you'll have same tensile stress in the steel wire, so it's a uniform distribution of the force. Okay, so that is a good thing because it's uniform force. The problem is once you put the concrete, you can't change it. Okay, once you put the concrete, you can't change the value, so you can't stretch further. Okay, so let's say you need to apply 20 kilonewton but by mistake you applied 15 or 18. Okay, and that's it, you can't change it because it's concrete harder, so the steel will not come or steel will not move. Okay, so that's a problem. So you need to make sure everything is correct before putting concrete in. And but it is a uniform, the calculation is relatively easy. Okay, and also there is another one in pre-tension. Normally the tenons or the wires should be within the section normally. Okay, normally the wires will stay within the section, it can't go outside in pre-tension. So but if you look at the post-tension, under the post-tension we have two different configuration. One is called internal post-tensioning, other one is external post-tension. Because in post-tensioning, the tendon or the wires can place outside. Okay, the wires or the tendons can be placed outside the tendons. Okay, so box girders, so you can put the girders in the hollow section as shown here. This is a half cut of the box girder, so you can see the wires or tendons can be placed. So technically you should be able to see the wires or tendons. Okay, so in this case we don't normally put the ducts there. Normally rather we put some provisions to insert the wires or tendons. Okay, there are no ducts here. they put some provisions like a holes so that the wire can be yes. So this is called external post tensioning. The other one is a wire inside internal post tensioning. Okay, so the advantage with the external post tensioning, since the wires or the tenons are placed outside, you should able to reduce the section dimension, or you should have hollow section. Okay, you should able to reduce the section height or size, or you should able to use hollow section so that the overall dead load, the self weight of the member will be reduced. Yes, if you have hollow section, the area will be less, or if you reduce a smaller cross section, the cross section area will be also reduced. So in external post tensioning, since the tenons can be placed outside, we should able to reduce the self weight of the beam, okay, by selecting either a hollow section or a smaller section. Okay. But in this one, internal post tensioning, you need to have the section, but still the section height will be much smaller compared to RC beams because less deflection. Okay, so under the internal post tensioning, again they give two types, bonded wires and unbonded wires. So the bonded wires and unbonded wires, if you look at the tendons, so tendons are normally inserted through a duct. Okay, the wires are, so you may have some ducts here, like something like a pipe. So when you insert the tendons and when you tight, after tightening, normally we will fill that gaps. Okay, so when you have the duct and you insert the tenon through the duct, so normally there will be some gaps between that. So we fill that gaps using grouted concrete with a high pressure. We fill that one, or sometimes we leave as unbonded. The bonded one, the design is easier. Okay, when you have bonded tendons or bonded wires, the design is easier because it's everything can be considered as a one single unit because everything fully bonded. If it is unbonded wires or unbonded tendons, the steel wires and concrete sections are not fully bonded, so the strain equilibrium may not work. Okay, strain equilibrium or strain equations may not work at particular cross section. What does that mean? Our analysis become more complex compared to the bonded wires or the pre-tension one. Pre-tension always inside and bonded. Okay, so the unbonded wires in the internal post tensioning and the external post tensionings have more complex analysis and design because the strain compatibility or strain equilibrium may not work as we did in the RC design or bonded wires. Okay, still they are in equilibrium, but the way to equate that one is slightly different because they are not bonded each other. So unbonded wires and external post tensionings are quite complicated. There are lots of empirical formulas available. to find out the strain in the tendon and the designing methods is slightly complex. So why we need the external post tensioning in unbonded wires if it is too complex? Okay. So unbonded wires have an advantage over the bonded wires, because if it is unbonded, you may able to re-tension the wire again after maybe 5 years. You might able to tighten the wires little bit, yeah, because it's not bonded. So you should be able to pull or stretch that one further, tighten it a little bit. So that is the advantage over the bonded and unbonded one. So you may readjust or re-tension. Re-tensioning opportunity is also available in the external post tensioning because it's usually unbonded. So if you look at the external post tensioning, as I told, the advantage is we should able to reduce the cell fate significantly. We should able to reduce the cell fate significantly because we should able to select a smaller section or a hollow section compared to other post tensioning, other pre-stressing members. Okay, pre-stressing members already smaller. Okay, pre-stressing members are already smaller compared to RC design. Within the pre-stress one, post tensioning, external post tensioning have further or can further reduce the section size, or we can select a hollow section. So that's a advantage of external post tension. So most of these new modern bridges, okay, use the hollow section girders, hollow box girders, so that they should be able to reduce the cell fate while maintaining the larger spans. You can see also, because the hollow section, you should be able to put the services. So this is not a pre-stressing wires, this is service, maybe electric wires or water pipeline. Okay, so they should be able to put some services through that hollow part. So the external post tensioning, especially with the box hollow sections, become more famous and nowadays. Okay, so the external post tensioning actually used in the early days as well, in 1950s or earlier, but it lost its popularity because the exposure, the steels are exposed to the environment. That means getting corrosion issues. So when you have corrosions, that will reduce or that will lose its strength. So they need to replace the wires very often because it's getting corrosion. So it lost its popularity in late 50s because of that issue. But it's again picked up in the late 70s or early 80s with the invention of these new technology that will reduce the corrosion issues. Okay, one of the things is I explained the epoxy coated steel that used in the Akibara bridge earlier. So that, so now you can see that bridges. This is the external post tension Parisian bridge, external post tension. So you can see this is also external post tensions one. You should be able to see all these ones have epoxy coat. So that, and also they sometimes they use some kava or kind of a cover, like a small tube kind of things. They insert over the tenons, the transparent covers. Okay, so that they should be able to see the corrosion issues and anything, so they should be able to monitor. So that's another way they use in early 80s, but nowadays they use the epoxies and other techniques, and also new treatment method in steel also give a better resistance against the corrosion. So they have lots of paintings and others, there are lots of techniques they use. So that's about the different pre-stressing techniques. Okay, so what we are covering in this unit, we are covering mostly the bonded wires. So the theory we are covering in this unit mostly with the bonded case, so that means it can be used bonded wires as an internal post-tensioning or pre-tensioning, so either will work. Those who are interested in the unbonded case, that means external post-tensioning or internal post-tensioning with unbonded wires, we should have used some different theories. Okay, the balancing of loads in the curvature, because the strains cannot be equate straight away because it's not bonded. So we need to find out the loads. We use the balancing of loads in each curvatures. It's a little bit more complex, so it's not covers in this one. But if you have any question, if you want to clarify a few things, you can ask. Okay. So I'm happy to answer, but we are not covering those things. Actually, I did my PhD in this external post-tensioning. So if you have any issues, please let me know. Okay, so now in this unit, the theories we are going to learn for next 4 or 5 weeks, mostly about the bonded wires. So that's here, the bonded wires or pre-tension one. Okay, so the theory can be used for both, but it can't be used in these ones, unbonded. Okay, so any question before we go into the next slide? Oh, all good. Okay, so if you want to design the pre-stress beam, we need to know a few things. Okay, so as we know, the main difference between this one and RC beam is we apply compressive force. We apply some compressive force to the beam. We apply some compressive force to the beam so that it will carry the full load. In that case, if you look at that one, so the compressive force actually change the tension zone under compression. Okay, because we know this will be the tension zone under the full load, so we apply some compressive force. So technically, if I ask you to design a PC beam, pre-stressed concrete beam, technically you should be able to tell few important parameters. Okay. For example, if you look at the RC design, reinforced concrete design, which we learned earlier of this term until last week. If I ask you to design a reinforced concrete beam for a given load, what will be your answer? You should be able to tell me what is the depth, yeah, depth of the beam. You should be able to tell, okay, this depth should be enough for this load using deflection check, and you should be able to tell me where you will provide the reinforcement, yeah, you should be able to tell me where you want to put the reinforcement bars and how much, what is the value for AST. AST will be provided as a depth of small d, effective depth. So you should be able to tell me, okay, put this much of kava and others, so technically the small d you should be able to tell me. Yep. And you should also be able to tell me the AST value, how much steel I need. Okay, so if I ask you to design, you will provide these information in RC design. So here, what are the information? So if I ask you to design a pre-stressed beam, technically you should be able to tell me the size of the or depth of the beam, okay, depth of the beam, as you did in the RC, and you should be able to tell me the amount of compressive force you want to apply, yeah, because here we apply compressive force, not the steel bars. We put the steel bars to apply compressive force. So we should be able to tell me, you should be able to tell me how much compressive force I should apply and where to apply. So these are very similar to RC beams. Okay, in RC beam also we have depth. In RC we put the location of the bars. Here also you need to tell me where to apply the compressive force, location of the pre-stress force. The next one, you should be able to tell me the amount of AST, how much bars I should provide. Here, amount of pre-stress. Okay, so very similar things. So I need to find out main objective. Okay, there are some other things, but the main things is to find out suitable section, pre-stress force, and the location we have to apply. So these are the three main important parameters I need to find out. So if we want to find out those three things, we need to develop a diagram called Magnell's diagram. Okay, Magnell diagrams. If we want to develop a Magnell diagram, you should know what are the stresses in the pre-stressed concrete member. Okay, because Magnell diagrams are use the stresses to develop that diagram, and we also need to understand the limit state design concept. Two different limit states we studied, ultimate limit state and serviceability limit state. So we should able to understand, or we should have clear understanding of the limit state design concept. Then we should be able to develop inequalities. Okay, inequalities and equations are different. Okay, I'll explain in a minute. Inequalities and equations are different. So we should know these first three. We should have clear understanding about the stresses, limit state design concept, and we should have clear understanding about inequalities so that we should be able to develop inequalities for the Magnum diagram. If you should able to do this once, then you should be able to use those inequalities to draw the Magnum diagram and find the suitable section, and from the Magnum diagram we should be able to find out how much pre-stress force we have to apply. So the development of inequalities will give you the answer for the suitable sections, required pre-stress, and the location of the pre-stress, the three things. Okay, so to get those things we need to develop inequalities. If we want to develop inequalities, we need to understand the stresses in the pre-stress. To get the full idea of the stresses, you should know this limit state design concept. Okay, so that's we will discuss these things so that we should be able to answer the first initial questions. What is the suitable section? How much pre-stress we need to apply? We have to apply. Okay, so before we go into that one, so just a quick overview about these inequalities and equations. Okay, so this is a common mistake even the students doing postgraduate. Last year or earlier we had problems. Okay, so just want to make sure you understand that hopefully most of you are okay. I don't say that all have problem, but just want to make sure. This is maths, okay, not structural design. This is not the structural design, this is maths. So if A is equal to B, minus A is equal to minus B, isn't it? That is correct?
Yeah.
Yeah. So this is correct. Yeah. 2A is equal to 2B.
Yeah.
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 1 upon A equal to 1 upon B. So all are correct? Yeah?
Yeah.
So if A greater than B, can we say that one? What about this one, is correct or wrong?
Wrong.
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 That is wrong. This one?
That's
Correct.
correct.
This is correct. This one?
Wrong.
Wrong. So here it is minus A, sign will change. 1 upon A also change the sign. So what does that mean? The first one will tell you you can't simply multiply by negative numbers. Yeah. So when you multiply by a positive number, the sign won't change. But when you multiply by a negative number, the sign will change. Okay. So if you have some inequalities, so if let's say this is okay, can I say this one? Is it correct? Is it correct? A is not 0. If A is not 0, can I divide by A? Is it correct or wrong? You say this one is okay. What about this one? So if this one is correct, can you say this one?
Yeah.
This is correct only if A is a positive number.
Yeah.
Okay? If A is a negative number, change the sign. Okay? So this is very important because this is what happened in the exams. Okay? They simply divide or multiply by something. If you don't know the sign, you can't multiply or divide. Okay? If you don't know the sign, so before you multiply the inequalities by some number, you should make sure it is a positive number. Okay? If it is negative, you need to sign. You need to change the sign. But you should make sure, or you should know the sign of the factor you are going to multiply the inequality. Okay? That is very, very important. Because in the past, the students sending email, okay, we couldn't get a feasible area, okay, for our project, and I asked them to send the file, Excel. Yeah, so in the inequality halfway, when they use an Excel sheet to draw the graph, so they use different values. Halfway through, the multiplication changes, but they use same sign. Okay, so they, without checking the values, they divide simply. So those kind of things should be avoided. Okay, so it simply happened during the project. We don't realize. So please take care when you look at that. That's important. Okay. Okay. So the other one is a graph. If I said y is equal to 2x plus 3. Oh, sorry. Can you see that one? Yeah. Okay. 2x plus 3. How to draw the graph? Yeah. So this one is 3, so it's somewhere here.
Yeah.
Positive, so it will go like that. Huh? So this is y is equal to 2x plus 3. Yeah. And if I said y less than 2x plus 3, or equal to. So if I ask you to draw that line, what you will do? What this graph? What you will do? So first draw the line first. Okay. If it is equal, it's a 3. If it is equal, it's a continuous line. If it is not equal, a dotted line. Okay. If it is equal, since it is equal, it's a continuous line. Okay. If it is not equal, only this one, so it should be dotted line. Okay. So okay, so this line is okay. So now they said y less than or equal to 2x plus 3. So this is y is equal to 2x plus 3. So less. So that means here. Yeah. So that means the whole region satisfy this inequality. Yeah. So for equations we have a single line. Okay. If it is a parabola or circle or whatever, if you have equation, you will have a single line. If it is inequality, you will have an area. Okay, an area for that. So if I ask you to solve y is equal to 2x plus 3 and y is equal to maybe 6x minus 1, okay, 6x minus 1, I ask you to solve, okay, using graph. So minus 1 is somewhere here, yeah, minus 1 is somewhere here, 6x little bit larger slope. So you'll have y is equal to 6x minus 1. Yeah. So the solution is this one. Yeah. So because this point satisfies this equation as well as this equation. Yeah. So if you draw that one, you'll get something like that. But if I ask you to solve y less than or equal to 2x plus 3 and y greater than or equal to 6x minus 1, what you'll do? So I need to draw the 6x minus 1 as we did here. This is minus 1, so that will go, yeah. So this is y is equal to 6x minus 1, okay. So it says greater, so that means this area, greater means above this line. So the solution will be given bounded by this one. So this is the solution. So this is the solution because it's less than that, greater than that. So again, you'll have an area. You'll have an area for the solution of. So any point within this area will satisfy this. Okay. So the solution for two inequalities will give an area. Solution for two equations will give a point, or maybe a couple of points if it is second order, third order, whatever. Okay. So we are dealing a little bit different territory in pre-stressed concrete. Okay. So you need to be a little bit careful and you write something, work out something in Excel. Any questions? Okay, so if you don't have anything, so just move on. So the first things to draw them to work out this McNeil diagram, or to work towards the McNeil diagram, we should have a clear idea about the limit state first. So in this one, in RC design, we use the deflection criteria to find out the section, yeah, isn't it? To check our assumption or to determine the depth of the beam or slab, we use the deflection criteria, isn't it? We use the deflection equation or deflection criteria for RC design. But in PC design, deflection is not a problem. We know the deflection is very small. So we try to eliminate the cracking. So we use the cracking as the criteria for the PC design to determine suitable section, suitable cross section, and to determine the pressure force. Okay, to determine the pressure force, and the suitable sections, we use the cracking criteria. Okay, cracking criteria means we don't want to have any cracks, so no cracking is the criteria we are going to use. No crackings. Okay, zero cracks. Okay, so if it is a cracking, again cracking comes under serviceability. Yeah, cracking comes under serviceability. Deflection, cracks and everything comes under serviceability. So we are going to use serviceability limit state, SLS, serviceability limit state, for our initial design. We did the same in slab and beams in RC design. So we use a serviceability limit state. Over there we use a deflection. Okay, over there we use the deflection. Here we are going to use cracks, cracking. But both comes under serviceability limit state. So we are going to use serviceability limit state for initial design. So we should use the load combination. We should use the load combination as per SLS, serviceability limit state. Okay, you know the load combination for ultimate and serviceabilities are different. So we should use serviceability limit state load combination for the initial design. Okay, so once we complete the initial design, we still need to check for ultimate. So over there we'll check for ultimate bending capacity or moment capacity and shear capacity. So for moment capacity and shear capacity, for moment capacity and shear capacity, we will use ultimate limit states. So the load combination will differ for initial design and the latter part of the design. Very similar to what we did earlier. Okay, load combination is different for deflection, load combination different for bending and shear. But we need to check for both. Okay. Okay, so for the initial design, as we said, no crackings, no crackings. We need to make sure there will be no cracks in the beam, but here we have two stages. One is transfer stage, other one is called service stage. What is transfer stage? Transfer stage is this one. You cut the wire, okay, or this one. You put the wire and stretch. So you transfer the load to the concrete. Okay. okay, from the steel to concrete. You transfer the steel load, steel is under tension, so we transfer the load to the concrete as a compression, okay. So that is called transfer stage. Normally that happen around 7 days, okay. 3 to 7 days, is depend on how quick that early strength gain happen. Okay, so that is transfer stage. So at that stage the beam will bend in opposite direction. Okay, normally if the beam bend downward, at transfer stage it will bend upward. Okay, so opposite to the normal bending. So that's transfer stage. The second one is called service stage, which is under full load, full service load. Okay, so we need to look at these two stages at the initial design. So we use these two stages to obtain a suitable cross section, and pre-stressing force and its location. For all three, we will use the initial design under serviceability limit state, and that time we will use these two stages. Once we finish those things, we will go to the ultimate check, that is bending and shear capacity. Okay, so we will continue this one next week, because tomorrow is a holiday. Okay, so any questions? Maybe we will stop here, but if you have any questions before closing the session, please ask me. There's no classes. No classes for tomorrow, so Wednesday is a submission. Okay. Let's see tomorrow. Sorry, let's look at the next week to continue this one. Okay. Okay, see you, bye.
Thank you, sir.